Okay, welcome guys. It's this is part one of three in a series, just kind of introducing the basic concepts of energy. Okay, so here we go. Let's get started. The first thing we should do is establish the definition of energy. So energy seems like this really basic thing. We use the word all the time, and in science, a definition that you'll see in a lot of, especially physics textbooks, is that energy is the capacity to do work, okay, and or produce heat. So those are the two things that we need to keep in mind when we're thinking about energy. So the first thing is that energy can be classified basically into two different categories. Energy can be thought of as it can be classified as kinetic energy, or it can be classified as potential energy. These are the two abbreviations that you see fairly often, KE and PE. Kinetic energy is essentially just energy due to motion. So if an object is in motion, whether it's a car going 60 miles an hour, a bullet traveling 1,200 feet per second, it's got kinetic energy. On the other hand, if an object is at rest, if it's just sitting there, not moving, there's no kinetic energy. Okay, so this one's pretty straightforward. Potential energy, on the other hand, potential energy can take a number of different forms. In general, it's energy due to either its position or to composition. I'll say a little bit more about what that means. Composition, that seems a little more mysterious, but position, I think we can all understand that, when a boulder is at the top of a mountain, or you've got a book that you're holding up in your hand, if you were to drop it on the floor, or if the boulder were to roll down the mountain, it's going to release energy in the form of gravitational energy, and that can be converted to kinetic energy. Another form of potential energy is electrostatic energy, so the attractive force that exists between electrons and protons. That's definitely a form of potential energy. Anytime you have a system where there's like a force acting between the particles, that sets up a potential energy. All right, so due to position, that's pretty straightforward. Composition, here's what I mean when I say energy due to composition. So we're going to be talking about a form of potential energy called chemical potential energy. And here are two molecules that demonstrate a huge difference in potential energy. One is, I'll start with the second one. This guy is aspirin. And, it's a pretty benign, friendly little molecule. You take it when you're feeling, when you have a headache or a fever, and you could burn this compound in oxygen in a combustion reaction, and you're definitely going to get some energy out of it. So there is some, there's definitely chemical potential energy here, but it's nothing compared to this high explosive RDX. This compound stores a lot of potential energy in the form of these three nitro groups. All right, you see nitro groups in a lot of explosives, and also particularly these nitrogen single bonds here, here, and here store a lot of potential energy. And when this thing is detonated, it releases a tremendous amount of energy. So in a sense, compounds like RDX are sort of like boulders at the top of a mountain. All it takes is a little nudge, and they release a tremendous amount of energy. So the energy coming from compounds like this is because of its chemical composition, and so that's what we mean by when we say potential energy due to composition. Okay, and then finally, I want to just formally introduce the first law of thermodynamics. You guys have known about this probably for years. You've heard of teachers say conservation of energy, right? Well, that I think you already have a good idea of what this means, and a slightly more formal way of saying it is that the total energy of the universe is constant. So one consequence of this is that energy can be neither created nor destroyed. It doesn't just disappear, but forms of energy can be interconverted. Okay, so now just to get a little bit more quantitative and to nail these things down a little bit more clearly. So kinetic energy, there's basically one formula, and this is it. So if you want to calculate the kinetic energy of an object, you just take the object, measure its mass, so m stands for mass, you measure its velocity, and then you square the velocity, multiply the square of the velocity by the mass, and then multiply by 1/2, and there you go. You've got the kinetic energy. So this one's relatively simple. It's the same formula for all kinetic energy. And by the way, in parentheses here, I don't mean to get too esoteric, but this is kind of interesting. This formula applies just fine. It's very accurate. But when an object starts moving fast enough, if it's getting near the speed of light, and so c is the symbol that's used in science for the speed of light. When velocity gets close to the speed of light, then you have to use a different form of this formula. You have to make relativistic corrections. And so the way we have it notated here is this just means that as long as the velocity is much, much less than the speed of light, then this formula is a-okay. The other form, potential energy. Now there are many different formulas for potential energy depending on what kind of system you're talking about. The one that we're probably most familiar with is like gravity, objects in a gravitational field. The book on the table, the rock on the top of the mountain. And when we're talking about potential energy due to gravity, it's mass times g. G is the acceleration due to Earth's gravity, and h is the height above, the ground, let's say. So here you go. It's a couple of nice formulas just to kind of make things a little more quantitative. Now let's take care of some of these. Now we got to take care of some of the common symbols. So m in these formulas stands for mass, and the SI unit of mass. And I don't know if you remember this. It's a lot of people want to say the gram, but it's not the gram, it's the kilogram. So that's one thing that we have to remember. V is for velocity, and the SI unit of velocity is meters per second. C is the symbol used in science for speed of light. And it's very fast. The speed of light is 300 million meters per second. Let's put that in terms of miles per second. The speed of light in miles per second, this is a good one to know, is 186,000 miles per second. It's incredibly fast. G, okay, so this was the acceleration due to gravity. And this is one that you probably have not run into yet. Acceleration due to gravity. This is one that you would learn a lot about if you take physics, which I hope you will. And the value for g at the Earth's surface is 9.8 meters per second squared. Okay, so and what that means is that if an object is falling freely near the Earth's surface, its velocity is going to increase by about 10 meters per second every second. So 10 meters per second. So that's why you got that kind of funny unit there. And then finally h for the potential energy expression up here, that's just the height, and that's in meters. Okay, so I just want you guys to know these terms. By the way, you are responsible for knowing the formula for kinetic energy. You need to know that, and you need to know these, what these symbols mean and their values. Okay, so let's talk about an example. This is a really cool application of those two formulas that we just saw. So what you can do is you can answer questions like this. So if you drop a bowling ball from the top of a 10-story building, you can ask the question, how fast is it going just before it hits the ground. Okay, so we're saying that this is this building is 35 meters tall. The bowling ball has some mass. We don't know what it is, and as it turns out, it doesn't matter what the mass is. Once I kind of start showing you how these equations relate, the mass just drops out, and the speed of a falling object is independent of its mass, which is really interesting. So first of all, when the ball starts to fall, okay, obviously the ball will start to accelerate, and it's going to get faster and faster and faster, right, until it hits the ground. So this is something that you know from everyday experience. And what's happening here is the potential energy at the top of the building is going to be converted to kinetic energy, and by the time it reaches the ground, the potential energy will reach zero. Okay, so it's at a maximum here at the top of the building, and then it slowly decreases until it reaches the potential energy is zero at the ground. Meanwhile, the kinetic energy is going to be increasing, okay, as it travels toward the ground. And finally, the kinetic energy will be at a maximum just before impact. And one thing that we know is that the potential energy at the top of the building has to be equal to the kinetic energy at the bottom. And this is a consequence of the first law of thermodynamics. You remember the first law says that energy cannot be created nor destroyed. Energy is conserved, and so yeah, this is how energy is conserved in this system. As the potential energy is lost, kinetic energy is gained, and this equivalence must be true. And so now let's just simply substitute the formulas that we learned from the last page and see if we can figure this out. Alright, so I'm going to just rewrite this. I'm going to put kinetic energy first. Okay, and now when we substitute the formulas in, we know that kinetic energy is 1/2 mv squared. Potential energy is mgh. And so if this first statement is true, then the second statement must be true, just because of the equalities. Now, what are we doing here? We're going to use this expression to solve for the velocity of the object just before it hits the ground. So all you got to do is just a little bit of algebra. So we multiply by 2 on each side, and that gives us mv squared equals 2 times mgh. And now notice that there's an m on both sides of the equation, and so from algebra we know that if we can simplify this, and we can basically cancel out the mass. If you're feeling a little queasy about doing that, just know that when you divide both sides by m, the m cancels on both sides, and so we get v squared on the left equals 2gh on the right. And you see how things are kind of simplifying a little bit. Finally, in order to solve for v, you take the square root of both sides, so that's 2gh square root. And so what I'd like you to do now is pause the video and substitute the values from the previous slide for g and for h. So that's 9.8 meters per second squared for g, 35 meters for h, and I want you to work this out and see what you come up with. Okay, so hopefully after you substitute it in, you got something like 26.2 meters per second. All right, and that's, you know, I don't even have a good feel all the time for how fast meters per second are, but what you can do, and I won't make you do this here, but if you convert meters per second to miles per hour, you get something around 59 miles per hour, which is pretty darn fast. That's like highway speed. And so, you know, when you drop something off of a 10-story building, it's going to be going really fast just before it hits the ground. Okay, so that's a really cool example of how you can use these simple equations for kinetic energy and potential energy to solve some really interesting problems. So now I just want to establish the SI unit of energy. So a moment ago we saw that kinetic energy, which is 1/2 mv squared, when you substitute the values in for mass and velocity, we have kilograms for mass, right? And for velocity, the units are meters per second, and that's squared. And so the SI unit of energy is kilograms meters squared per second squared, right? Because that's potential energy, and that's what we end up with. If you do the same thing with the potential energy, I'm not going to do that here, but if you substitute values in for this expression, you'll arrive at the very same collection of units. This is a kind of a crazy looking set of units, and the good news is that in science, we replace these with the joule. And so any kind of energy that we are going to be talking about here in thermochemistry, we're usually going to talk about it in terms of joules, and this is the SI unit of energy. There are other forms of energy that I want you to be aware of, and the main one that I'd like you to know about is the calorie. Okay, and so 1 calorie is equivalent to 4.18 joules. All right, so that's an equivalence that I would like you to know. The joule is smaller. It's about 1/4 the size of a calorie, so it takes just a little over 4 of them to equal a calorie, and so that's an equivalence I'd like you to kind of keep in mind. By the way, the abbreviation for calorie is CAL. All right, okay. So some simple conversions. For example, if you were given 217 calories and you were asked to convert that to joules, all you got to do is take the 217 calories that you were given and then multiply by a conversion factor where you're going to use this equivalence that we just established on the previous slide. So since we want to cancel the calories, right, you want to put 1 calorie on the bottom, and the 4.18 joules, goes on top. And why don't you go ahead and multiply that out, and we'll see what we get. Okay, did you get something around 907 joules? And you'll notice that this number, 907, is about 4 times larger than this. Okay, because remember, it takes about 4 joules for every calorie. Okay, so just kind of be sure that you're going to be okay with converting between those units. Okay, so this is the last slide, just to wrap things up. All right, so what did we go over? We talked about the definition of energy, so make sure that you can state that simple definition of energy. It's the capacity to do work and or produce heat. There are 2 forms of energy basically. There's kinetic energy and there's potential energy. We now know the formula for kinetic energy, so that's something you've got to know. We know that potential energy is energy due to either position or to composition, like chemical composition. And then finally, there are different units of energy. The SI unit of energy is the joule with the abbreviation capital J, and there's also calories with the abbreviation CAL. Okay, thanks guys. See you at the next video.